Yeah.
Yes.
So I emailed you yesterday, I guess, or the day before yesterday, because none of the lectures have been uploaded for
Yeah,
last
yeah.
week.
So that's correct. As I said last week, we cannot upload the lectures to YouTube, or excuse me, to Canvas right now. There's just no memory. So,
How about the whiteboards?
well, the whiteboard should be there. I post those. I checked that this morning. Are you still not seeing whiteboards?
Uh, just a moment.
I mean, check that right now. I was under the impression all the whiteboards were there. They look, yeah, the whiteboards from last week are there.
Yeah.
Yeah.
they're there
But I will be posting. So what I'm doing is, since since the lectures are so long, they're like an hour, some longer. You can't even upload them to. I have to break them apart. So I'm in the process of doing that. Once I figure out how to edit them properly, then what we'll do is we'll probably put them on YouTube for you to check out. But right now, I can't think of an efficient way to get multiple lectures up. And don't forget, I have a couple classes, so I'm trying to do this for all my classes. And so right now, the best we can do are these whiteboards. But I hope to have this problem resolved in the next day or so. So hopefully, this is the plan. So hopefully all lectures will be uploaded by the end of the week. Don't forget also, and this is, it's a holiday week for the Catholic religion, so there's no class this week. You know, I call these classes, but whatever. So no classes Thursday or Friday. So just to keep in mind, we won't be meeting virtually. So keep that in mind. That can give you, it hopefully gives you guys some time to catch up and get some things situated. Does anybody else have a question? Hopefully that also gives me time to get these lectures up.
Yeah. Could we go to practice at 10?
Mm-hmm.
Question number 4. Like there's question B, C, and D. What's the formulas for doing that?
All right, give me 1 second. You said practice set number 4. Give me a moment to pick it up. Why did I just lose my? I know you said home practice at 10, number 4.
Yeah.
And which ones did you say?
B, C, and D.
Okay, so we did B in class. We did T log T, or probably did X log X, but we did those in class. So here's the trick for how to handle those. So look back, probably 2 classes ago we did those ones, or maybe it was Friday, I don't remember. So let's check that out. So so if you need help for homework number 10, so if you look at 4, say B, so you need to rewrite as so right now you have T squared log T, but you need to rewrite this as log of T over T to the negative 2. That's one way to do it. Then L'Hopital applies. So you apply L'Hopital's rule. And so this limit under L'Hopital's rule becomes the limit. You differentiate the numerator, which is 1 over t. Differentiate the denominator, you get negative 2t to the negative 3. Okay, and now you just have to do some algebra. This is this limit. Well, it shouldn't be infinity, that's 0. So this limit as t goes to 0. And then just do the algebra. What are you left with? You're left with negative 1/2 times. If you flip this negative exponent, this just becomes times t squared. So that's algebra. I'm not doing anything fancy. And then when you take the limit, you just get 0. So the limit is 0. I don't know. Again, it might take a moment or two of your time to think about how I went from the fraction to down to the negative 1/2 t squared, but it's merely algebra. There's no calculus involved there. The only quote unquote calculus is the L'Hopital step. So you have to remember the derivative of the log, and then you also have to remember that the chain rule. Well, I guess it's not the chain rule per se, but we're differentiating t to the negative 2. So that's how you do B. Does anybody have a question about that or a comment?
So basically, when it's a product, so the first function goes down while the other one goes on top, right?
Well, okay, you're making a connection, which is correct. Not all the time, but sometimes. So I believe you're saying that if you have a product,
Yeah.
that you can do this trick, and that's correct. So this rewriting, it often works with products. So the original limit is the product, and in order to apply L'Hopital's rule, we rewrite it, and we rewrite it as a fraction. So that is a trick that works sometimes, not all the time. It will also work for other problems. So this trick will also be very useful for C. So for example, you do something similar for C. So for C, the idea is similar to B. That is, you take x squared sine of 1 over 5x squared, and you rewrite it. This is sine of 1 over 5x squared, and this is all over x to the minus 2. Now L'Hopital applies. So you have to make this observation first, and then you can apply L'Hopital's rule. The same trick works for G. If you're creative with it. Okay. And then the last question you asked was about D. Well, we did one almost identical to D, only we took the limit at 0 instead of infinity. And this one needs the trick of the following. You need to write this creature. So we talked about this last week, this property of logs and exponents. You need to write this as e to the log of this thing. And this can be written as ex times the log. So this is not an easy limit. Ones like D are quite difficult, but we did an example very similar. It's something that you should be able to do. For most students in this class, it's going to take you a while to understand. These are not necessarily easy. Some of these are easy. These three particularly require some ingenuity. But these are skills that aren't just tricks. These are themes that pop up in many areas. This happens to be one of them.
So after the
What's that?
after that last step you did, right? We
Yeah,
used the other step you told us, right? The one we used in B.
correct. Yep, it's almost identical to B. That's right. So yeah, from this point on, it's almost identical to B. Now the derivatives are a little different, but it's the general theme is the same.
And then I just had another question. Let's
Yeah.
say if we have 1 over x, right? And then they said the limit as x approaches to infinity. Does it mean every time 1 is over infinity, it's a 0?
Well, okay, so no, you're sort of thinking of that in a very naive way. I think so. I think what your comment is the following. So this is an important fact. So we should pay attention to this. When you write something like the limit as x goes to infinity of 1 over x, when you say that this equals 0, what does this mean? This means that as x becomes quote unquote larger, 1 over x gets closer to 0. That's what that means. They're never equal. It doesn't make sense to say 1 over x is equal, or excuse me, 1 over infinity is 0. But that's what your mind needs to think. So what you say, a better way of thinking about that is 1 over very large is equal to very small. That's the way you need to think about it.
Okay.
But it's meaningless to write 1 over infinity. And remember, infinity is a symbol that we've invented to describe the process of never ending. So when we say x goes to infinity, that is a notation that humans invented so that the reader understands that we're letting x get larger and larger and larger and larger. It's growing and growing and growing. It's never stopped growing. That's what that means. So if you look at the graph, if you go back to what the graph of this expression looks like. I mean, go back to when you were in algebra class and you studied functions like 1 over x. What does the graph look like? Well, the graph has a vertical asymptote and it has a horizontal asymptote. So this is the curve 1 equals y over x. So again, these are delicate issues that, aren't the easiest things to learn. They take plenty of time and experience to really get a solid understanding of this. I don't know if that makes sense, but that's, off the top of my head, that's the best way I can think about describing it. Does anybody have a question about this? Does that make sense, Shobit? I don't know.
Yeah, it does. And then something else is like, is there an L'Hopital's rule? You still get an undefined answer?
For E?
For E, but like an equation, right? Any equation that if you use the L'Hopital, is it possible that even if you use the L'Hopital's rule, right?
Sometimes you have to use L'Hopital's once or twice. Sometimes you can use it forever and ever and you don't get anywhere. It doesn't always work.
So meaning it's a repeat process, right? You can use L'Hopital as a repeat process.
It's possible that you can just get in an endless cycle of L'Hopital's rule and it gets you nowhere. that means either one of two things. You set it up wrong or it doesn't work.
Okay.
Like if you look at G, there's a correct way to do G and there's an incorrect way to do G. So you could think of it that way. Some way in similar with other problems. Sometimes there's a correct way to do it. Sometimes there's an incorrect way of doing it. But yeah, you can definitely get into a cycle where L'Hopital gets you nowhere. And that means either you used it incorrectly or it's not going to work. It could be one of those options. Does that make sense?
Yeah, it does.
Okay. Any other questions on this homework? All right. If you guys don't have questions, then we will move on to our next topic.
What if we have a chain rule in
You'll have a chain rule in D.
so we just do it the way you just showed us, right?
Yeah, I mean, if you have a chain rule, you do it. Anytime you have a composition, like in D, where the exponent is in the base and in the exponent, you have to use that exponential trick. That's how you have to do it.
And if we have three products, we try to make it two, right? Impossible.
Well, where do you see three products at? I didn't give you an example like that.
No, I'm just like asking, just for knowledge.
Oh yeah, that's what I would do. I would break it down. You can always write the product of three things as the product of two things, and then apply it twice.
Okay.
Okay. Does anybody have a question about this before we move on? Okay, so then we're going to move on to something different. So let's on to the next topic, which is going to seem completely ridiculous, but are completely non-associated with what we've been doing, but it's actually related. So it's time to talk about area. So to do this, we look at a classical problem. In modern terms. So if I said to you, first off, define area, none of you could do it. I said this to you the very first day of class. In fact, I think I asked you guys to write on a sheet of paper, what is your definition of velocity? What is your definition of area? And it's sitting in my office right now, actually. So at that point, none of you were capable of giving me a definition of area. And right now, you're likely not. And that's not a knock on you. That's not me insulting you. That's because the idea of area is a very delicate issue. Sure, you guys understand that the area of a rectangle is its length times width. You even learn as a kid that the area of a circle is pi times the radius squared, even though you might not know where that comes from. But in general, to define area, it's not an easy thing to do. And that's actually what we're going to do. So we will define area using the area idea that a rectangle So if I just draw a rectangle, we typically define its area as its length. You know, you associate one side with a length. Perhaps we'll call this the length, then we'll call this the width, and if we multiply them together, we call it the area. So this is the idea. Given a curved shape, how do we define its area? So here's the problem. So given a region in the plane, define its size. So what do we call its size? We call its size the area. So suppose I have the XY axis, and let's suppose I have some arbitrary region. All kinds of chaos happening upstairs. So what is the area or the size of the shaded region? So this is a question that has sort of given mathematicians and philosophers and scientists in general, it's given them a very difficult time as far back as we have written history. It's not an easy problem to answer. And if you ponder this for a second, you'll realize you never quite studied this problem in your entire life, even as a kid in school. You studied squares and rectangles and triangles. You studied combinations of those, but you never studied the size, the quote unquote size of an arbitrary region. Oh, by the way, there's a slight typo here. You guys should have me fired or drawn and quartered for poor drawing. This is not Y here. This should be the X axis. Does anybody have a question? So, as we said on the previous page, and this is important too, we need our definition to agree with elementary formulas from, so we want our definition to agree with elementary formulas for rectangles, triangles, etc. So that's what we want to do. Does anybody have a question? Okay. So what we're going to do is we're going to study what you might think because of your your days in school, the most basic function whose graph is a curve. So think about how you learned about functions. You first learned about lines, y equals mx plus b's. Now, if you look at their graph, their graph is a line, and so if you think about what kind of shapes they might generate, they would generate triangles, and they could also generate rectangles. We don't want to generate a shape that has boundaries that are straight. We want to understand what happens when the boundary is a curve. So here's what we're going to do. By the way, does anybody have a question before we move on? Okay, so let's motivate with a specific example. You guys know this is how I like to roll. I like to give examples. So to motivate, let's generate a region with a curved boundary. By restricting what I'd like to do is I'd like to restrict y equals x squared to the interval 0, 1. So let's draw what this picture might look like. This is a parabola, an old friend of ours. So what I'm going to do is I'm going to mark off some this one, and then we'll call this one. So what does the parabola look like? Its graph looks like this. Oh, got to be a little more careful. I'm not drawing that properly. Let's use a different color. Woo. Don't erase it all. Aw, you jerk. I hate this. They won't. I wanted to keep most of that. The third time is, of course, the charm. Okay, that's perfect. So we have this point right here. This is the point 1, 1. And what I'm saying is we are interested in this region. So what we're interested in is what we want to study is we want to ask ourselves, what is the area of this region? So I'm going to shade in this. My marker doesn't fail me. So if I want to think about this region, I want to know what is this region that I've shaded in purple. So this region has 2 straight line boundaries and 1 curved boundary. So we might say, okay, how can we study the size of this? So we want to assign a size or area to this shaded region. So a couple things that we can clearly see. For example, we could say, okay, well, there's clearly this region has to be less than a half. You might say, well, how do I know that? Well, we would want it to be at least, because the area of the whole square that it lives in is 1 by 1. And if I cut that square down to the diagonal, it's inside a triangle. And so we would expect that whatever this size should be, it should be a number that's no bigger than a half. So you might want to think about that, as we expect the area to be less than a half. Again, if you don't see that, think about the triangle that goes from 1, 1 to the origin, and look at the area of that triangle. Okay. So what we'd like to do is we'd like to figure out a way of to sort of define this area. How can we come up with a number? And again, we want this to be in agreement with our previous knowledge about what we call polygons, like squares and triangles and rectangles and, you know, pentagons and octagons. We want those ideas that we learned about in elementary geometry, we want those to be in agreement with what we have here. So how can we do that is the big question. And so one of the ideas, if I said for a while for you to think about how you might do it and brainstorm, and if you got together with your friends, and after a while, what you do is you come up with some interesting ideas. Some would be good, some would be not so good. But one idea that has stood the test of time is to approximate with rectangles. So what does that mean when that beeps? Does somebody have a question? I'm hearing a beep. I don't know why. Maybe someone's entering or leaving. I have no. So one strategy is to approximate with rectangles. So to do this, so here's one way to do it. So we can divide the interval 0, 1 into n equal pieces. Now, if I want to divide this into n equal pieces, what is each one of their widths going to be? Well, what we're going to do is we call it a name. We typically call it delta x. This is like a triangle. And what is their width? Well, it's going to be 1 over n. Next, construct rectangles. by computing the following. Right, so maybe computing is a bad word. Let's not write computing. So computing is a poor way of saying this. So we want to construct rectangles. So let me phrase it this way. We have a curve. We go to the previous slide. We want to take this interval 0, 1, and we want to break it into n pieces, maybe 4, maybe 20, maybe 200, maybe 10,000. And then we want to construct rectangles. So one way we might construct rectangles is we might construct rectangles by looking at points on the curve. So what points are on the curve? Well, that is the curve y equals x squared. So so we might want to plot some points. What are they? Well, we might want to plot the point 1 over n, comma, or excuse me, not 1 over n. Let me. Okay, yeah. So we'll do it that way. So 1 over n, comma 1 over n squared, and then we might want to plot the point 2 over n, comma 2 over n quantity squared. And we might want to do this for all n points. Now, what's the very last point? The very last point would be the point 1, comma 1. So this is going to be very confusing right now. Don't worry, you're going to be confused, but we're going to do it in a specific case right now, and hopefully it eases the confusing. So let's look at this in a case where we don't have n, but we have some fixed number for it. So let's go to the next page. So here's a very important example. Let's look at the example where n is equal to 4. So the first thing I'm going to do is I'm going to draw a number line of 0 to 1. And if I want to break this into 4 pieces, what are these points? Well, this is the point 1/4. This is a half or 2/4, and then this is 3/4. And each one of these distances is my delta x. So remember, delta x, by definition, is 1 over n, which in this particular case is 1/4. So now let's draw our region again, and let's see how these rectangles might be constructed. So if I get my curve, so let's think about plotting these points first. Let's imagine this is, whoa. Imagine that's 1, imagine this is 1. So here's our point 1, comma 1. Now what's our curve look like? Well, we remember this is a parabola, so let's see if I can do this without 3 attempts. Why did it stop? I hate this. So the curve is going to look, I don't know why. I'm having technical difficulties. I don't know whose fault it is. Who should I blame for this? Me or the computer? So the curve looks something like this. And so if we, again, if we went to Desmos or GeoGebra, we would see this in a much better way. But let's now look at this point. This is 2/4. This is 3/4. This is 1/4. And so you might be asking, oh, Grady, why are you writing 2/4 if it's 1/2? Well, I want to write 2/4 because there's a pattern that's hiding out. And I'd always like you guys to be thinking about patterns. You might also want to note for the pattern that what is another way of writing 1? Another way of writing the number 1 is 4/4. And if you really want to get specific, what's another way of writing 0? Notice that 0 can also be written as 0/4. So the reason I write that is that you notice a nice pattern here. I have 0/4, 1/4, 2/4, 3/4, 4/4. And so what I'd like to do now is I'd like to create my rectangles. And I said I want to plot some points. So let's get a different color. Let's get this purple. And I said let's plot this point, this point, this point, and of course this point's already plotted. So you can easily write down what each one of these coordinates are. So let's take a different color. We'll take this light blue. What is this point right here? Well, this is the point 1/4, 1/16. How did I get 1/16? Well, I'm squaring it. You square 1/4, you get 1/16. Remember, this function is squaring. What is this point? This is the point 1/2, you square it, you get 1/4. And then what is this point? This is the point 3/4, 9/16. Does anybody have a question? Now, some of you have probably seen this idea before. If you had any type of calculus in high school, you have. And what a mistake I don't want you to make is for you to think, oh, I've seen this, this is easy. Because it's all we're doing right now is a very intuitive argument. When we do this in precise terms later, it's, you know, the difficulty level is going to go from here through the roof. And I don't mean that to scare you. I mean that to keep you honest and humble. That right now we're doing a very basic example, and I can't emphasize enough how important it is, at least for me, in my head, for you to do whatever it takes to try to understand this example. Although my kid's on, I don't know if you can hear her. She's upstairs crying. The ceiling is going to collapse. Okay. So what can we do now? Well, how do we build our rectangle? Well, we can build our rectangles using these points. So there's two ways to do this now. So let's write this down. So let's take our marker. So given these 2 points, there are 2 ways to construct rectangles. So let's look at them. Hi, Ricky.
Sorry, she wanted down here.
I understand.
Where do you want to go?
Outside.
Okay. Slide.
No, she said outside.
Oh, we can't go outside. No, she said slide.
All right, we have visitors. All right, so how in the world can we figure out? Hey, I'm not going to be rude. This thing is going to work. I mean, I don't mean to be rude.
All right, come on. We gotta go up.
Well, she can play. It's okay. So hold on 1 second.
I'll take her back up, but I mean, she's
All right. Watch your mouth. That was good. Anyhow, so what are the two ways that we can do this? You're going to have to maybe deal with some children. Ricky, go upstairs. Ricky, upstairs. I'm back. We have chaos. Swearing and cussing at kids. This is never good. All right. But it is fun. Okay, so what we want to do is we want to think about how we can construct rectangles. And maybe you might even be thinking, what do we care about rectangles for right now? Well, again, we want to think about how we might imagine this region, how we might define it. So here's what we're going to do. We go to the next page and we're going to draw. I wish I could copy and paste this picture. It would be so ideal if I could. Let me try something. No, it wants me to move it. Why can't I just do the whole picture? Well, I got an idea. Well, no, can I insert? No, you can't do that. This is terrible. All right. We got to find better software. Okay, so let's draw this thing 2 times now. We're going to draw it over here. Whoops, I didn't want to use it that way. So let's draw this one, and then we'll draw a very similar, hopefully almost identical thing here. So we're going to do this very carefully and detailed in this case, and then we're going to sort of ask you to envision the more subtle cases. So once again, we have 1 and 1, and then here's 1, and then here's 1. Let's put our what we call our partition. That's the fancy word for this. Let's write this down. So this construction is one that we will do more, not just this semester, but also in Calc 2 and Calc 3 if you ever make it to those promised lands. So let's sort of think about how this looks, something like that. Something like this. And so we have these points that we drew on the previous page. I'm not going to label them again, but we can at least draw them. Would I be teaching Calc 2 this fall? Of course. And in the summer. By the way, you guys, if you can, you should take summer classes. I mean, I'm not saying everybody can, but if I were you and you can, I would take them. Just my 2 cents. But yes, I teach Calc 1 and 2, sometimes Calc 3, so take it. Does that answer your question, Michelle? Although maybe that's bad, Michelle. Maybe you're like, no, I refuse to take it with O'Grady. He sucks. He's mean. Okay, so these pictures are somewhat what I'm trying to do. So let's think about how I can construct these rectangles. So let's use, the first way I'm going to construct rectangles is I'm going to start at each of these 4 points, and I'm going to make a rectangle like this. These are supposed to be straight lines. So give me this eraser. You'd be amazed how difficult it is to draw a straight line. Although maybe you wouldn't. I'm trying to be as clean as I can here, guys. I apologize. It's not as easy, and I've never really used this stuff before, so I'm learning just as you guys go. So that's one way to construct my rectangles. Another way to construct them is, instead of starting with this pink point, what if I start over here? Here's just a line. Can anybody hear my kid up there? She's singing Moana. It's hysterical. This is, you would. I'm gonna have to fix this. This is a bit, the scale is a little suspect here, my friends. So bear with me. Now, one of the things I didn't do as well, hopefully when I show you some software, we'll do this on the computer, it's a little better. These drawings are not accurate as they should be, and I apologize for that. It's mostly because I'm trying to do it on this stylus thing, and I don't know. I don't know what the best way to learn this crap is online. I'm learning as you're learning. This is not ideal, but we're doing the best we can. And as you know, that's all we can do sometimes. So here's the thing that we can say, though, just from looking at this picture. So imagine you're not in calculus. Imagine you're in 6th grade. And I say, okay, here we go. Let's look at the area of the 4 rectangles on the left, and let's look at the area of the 4 on the right. Although there's really not 4 on the right-hand side. There's just, because this one has height 0. So we can compute these areas, though. So if I do that, let's look at something. So here's what we have. So we have 4 rectangles of area. What's the first one? Well, they have a length and a width. So let's write it like the following. Their height, so this would be 1/16 times a 4th. Plus the height of the next one is 1/4 times a 4th. The height of the next one is 9/4 times a 4th, because that's its width. And then the last one is 1 times a 4th. So if you wanted to clean this up, you could factor out the 4th, and you're left with 1/16 plus 1/4 plus 9/4 plus 1. And then over here, what's the area here? On this side, you have 4 rectangles of area. So here, the first one's height is 0 times 1/4 plus the next one's height is 1/16 times 1/4. And by the way, no one yelled at me so we're going to have to, sometimes I forget that maybe you're afraid. So you have to switch this. I didn't follow my pattern over here that I was doing. So perhaps I should fix that before we get too far. The way I was doing it was like this. So what are the heights of my 4 rectangles over here? It looks as if I only have 3 because the height of 1 is 0. And so then this is 9/4. Whoa. So one of the things that I would encourage you to do is, I skipped one. What I would encourage you to do is look at the patterns that are happening here. So if I factor out the width of each one of them, which is 1/4, you're left with 0 plus 1/16 plus 1/4 plus 9/4. So it almost looks similar to the other side. Does anybody have a question?
Wait, why is 3/4 9/4 instead of 16? If you're finding
Because I'm losing my mind. That is an honest mistake. I don't know. That's why you're here, so you can fix that for me. That would have been real bad had we not fixed that. We would have had issues. So that should be 16. This should be 16. And then we have to fix it downstairs as well. Does this make sense?
kind of.
Okay, well, it's not easy to learn, but we're gonna make we want to make it a little different now. So here's what we would imagine. First off, on the right hand side, we would expect that if we add that up, we get a number. So we can do the arithmetic here. What's the arithmetic on the right hand side? Well, you can either go to a calculator or you can do whatever. Suppose we go to a calculator for the time being. Maybe you just go to, if you'd like, you can go to Google or your handheld calculator. It doesn't really matter what calculator you use. But suppose I go to a calculator and I add these numbers up. I'm going to get something. I'll do this real quickly. You could do this on your own. In fact, I would highly encourage you do it on your own.
I guess it's 14/16.
What do you mean 14/16?
When you add the inside
Are you talking about the one on the right or the left?
number, the one on the right.
Well, when I add up the one on the right, I am getting 7/32.
You mean also after multiplying, right? I meant the inside part only.
Oh, maybe, yeah. You have to multiply by the 1/4, yes. And then what happens on the left-hand side? Well, you have a slightly different sum. You have to, when you add that one, everything up, you get
15 over 32.
That's correct, yes. Okay, so I did that one by hand. And so on the next page, I want to summarize this. And again, I can't emphasize enough how important I think it is if you want to learn this, for you to study this what I just did. Even if you think you understand it, I would encourage that you study it. So I want to rewrite this in a different form. Clearly, 7 over 32 is smaller than 15 over 32. So, but that's okay. Looking at the pictures, if we take our 6th grade brain and say, okay, what can I deduce from this? Don't think about the numbers. Don't think about all the fractions and stuff. Just think of the picture. What could the 5th or the 6th grader deduce? So what they can deduce is the following. Just looking at the pictures. So let A be the area we originally asked about. So the above pictures and calculations, what do they show? They show the following. They show that the area we're interested in is less than 15 over 32, but it's greater than 7 over 32. So where am I getting those numbers from? Just from the previous page. Does anybody have a question about this? Going once, going twice. Now that's a very crude estimate, but it is an estimate. And it's better than what we found before where we said it has to be less than a half. So this is a decent estimate. Does anybody have a question? Comment, concern? Okay, so a couple of things you might ask. You might say, well, what was special about 4? Well, nothing. 4 is actually not that great. The only good thing about 4 is that it's easy to draw and it's easy to calculate. But what if instead of 4 rectangles, I said I want you to draw 40? That would be a pain. However, if we study this example with 4, we can come up with a formula because there's lots of patterns living in this creature. Lots and lots and lots of patterns. So the first question we might ask is, what happens when n equals 10 or 100? Or anything? Well, here's what we can say. If we study the previous example, we see a pattern. And it ain't just any old pattern. It is a beautiful pattern. So what do I mean? Well, if I study this, if I go back to the previous page, I could write these numbers slightly differently. And let's help you try to see that. So note, I wrote 1/4 and then I had 1/16 and then we had, what was it, 1/4 and then we had 9/16 and then we had 1. So I'm getting that from 2 slides ago on the left-hand side. But I can rewrite this, and then there's a pattern that is screaming at me. If I rewrite this, if I write this as 1/4 squared, and then 1/4, that's the same as 1/2 squared, but that's also the same as 2/4 squared. And then 9/16 is the same as 3/4 squared. And then 1, believe it or not, is the same as 4/4 squared. So now when I choose to rewrite it like this, I see a clear pattern. And more is true. I can rewrite this in an even prettier way. Before I do that, please ask a question if you must. Does anybody have a question about this? So notice that I can even now factor 1/4 squared out. So I can write this as 1/4 times 1/4 squared, and what's left? 1 squared plus 2 squared plus 3 squared plus 4 squared. Ain't that something? So we can even beat the dead horse one more time. This is 1/4 cubed. And this is times 1 squared plus 2 squared plus 3 squared plus 4 squared.
Wait, how do you get in the second one, right?
Yes.
How do you get 2/4 and 4
Well, what's another way of writing 2/4?
half?
Well, what's 1/2 squared?
Okay.
Right? And the same thing with 4/4. 4/4 is just 1. But if I rewrite it like this, I get a pattern. These are all the same. If you went to a calculator and added up all 4 of these lines, each one of them is going to give you the same number. Now, why would I want to write it like this? Well, because if I write it like this, there's a pattern. And I can take advantage of it. This extends. There's nothing special about this pattern. This pattern is true for 4. So in general, we have the following. Now, this is going to maybe drive you crazy, but you're going to have to bear with me because we're running out of time. I don't want to. I want to end this where we can still make sense of it. So for n equals 8, what you would have is you would have a very similar thing. You would have the following. So inside you'd have 1 squared plus 2 squared plus 3 squared all the way up to 8 squared. And then what would be out front? What would the widths be? Well, all the widths are going to be 1 over 8. But what am I factoring out? I'm also factoring out a 1 over 8 for each one of these guys. So I would have 1 over 8 cubed. So let me write that a little cleaner. That's so you'd have this formula. If n was 20, you'd have 1 over 20 cubed times 1 squared plus 2 squared plus 3 squared. Up to the 20th squared. So what does this suggest? Well, it suggests the following. And you can experiment with this to convince yourself, but it's absolutely true. Thus, for each n, the actual area we want is going to be approximately 1 over n cubed times 1 squared plus 2 squared plus 3 squared all the way up to n squared. Now, it is, if you want to understand why this is the case, you're going to need to repeat that problem we did with 4 and do it for 8 and 6 or 8 or 10 until you get a feel for how this pattern behaves. It's not hard to see it, but you have to do it yourself. You know, you're not just going to, well, you can trust me if you want. Excuse me, but if you want to really see how it works, you're going to have to do everything on your own. So let's make a table.
But if we use that, don't we get another different answer compared to
Doesn't
what
matter, right? That's exactly right. So here you go. You can do the same thing, but what's going to happen is if you do it the other way, what was the only difference? What was the difference between the other way?
8 or 15?
So similarly, use the other formula. That's right. So if you use the other formula, so if we use the other set of rectangles, what do you get? Well, you get that A is 1 over n cubed. Now, the other set started at 0. So it was 0 squared plus 1 squared plus 2 squared. Now, we didn't go all the way out to the last one. What number precedes n? Well, what precedes n is n minus 1 squared. And if you want to be very, very specific, Shobit, you can say this. More specifically, where does A live? A is always less than something and greater than something. Well, we know that it's always greater than this guy. We know it's always bigger than this guy, and we know it's always less than the guy on the previous page. And that's pretty clear just by thinking how many numbers you're adding up. So what I'm going to do before we end is I'm going to calculate a bunch of these. And then I'm going to show you a picture, and I hope that it gives you some intuition, and I hope we can build on it. Before I do that, does anybody have a question? By the way, some of you might even know another shortcut. Maybe you had some excellent teachers who showed you that there is a formula for these sums. Does anybody know what the formula is? 1 squared plus 2 squared plus 3 squared all the way up to n squared. There's a very nice formula for that. So what I'd like to do to finish is that let's make a table. Let's do this. So on the next page, if you guys don't have any questions, I'm going to sort of put a bow on this by writing down a table. Does anybody have a question? All right, so let's do that. So the next page, we'll do that. And so here are the results for different values. So what I'm going to do is I'm going to make a table. I'm going to say here's n. And then let's put over here, we want to do our approximation. So let's draw a line. This is going to be so much fun. And then, of course, you're going to be like, where do you get these numbers from, O'Grady? So first off, we started with 4. So let's do our first one. Our first one was 4. If you go to a calculator and plug these numbers in, which I'm technically not going to do right now, but I'll show you a way you can do this real quickly on next time we meet. So if I go to my calculator and I say, okay, I don't want this. Bear with me. I just lost the thing that I was trying to graph. And I actually built one of these things for you guys. Give me 1 second. My calculator's not working. Bear with me. Oh, yeah, that's why. So as you guys saw when we did this before, what did we get? Our first value, I'm not going to write fractions, I'm going to write decimals. So what was A? We knew A was less than 0.46. And we also found that it was greater than 0.218. So maybe we'll do 3 decimal places just so you can see the pattern. All right, so let's jump up to, we'll double each time. So we'll do 8 rectangles now. If I go to my calculator and do 8 rectangles and I compute these guys, I get that A is less than 0.398, and then I get that it's greater than 0.273. So let's go to, say, 40 rectangles now. and then we'll do, say, 100, and then we'll do 500, and we'll do 1,000, and then we'll finish with 10,000. So we start to see what's happening here. So if I do 40 rectangles, I get that A is greater than 0.321, and we're going to get that it's less than 0.346. So again, how am I getting these? I'm plugging these numbers into a calculator. I already have the formula set up. So for 100, I get A is less than 0.338. And then I get, if I use 100 rectangles, I am trapping my area between these two values, 0.328 here. So one of the things that you might start to observe is you are seeing what? You are seeing some sort of limiting thing happening. What is happening to my estimates above and below? They are actually coming towards each other. So if I go to 500 rectangles now, over here I get 0.332 is less than my area, and then I get that my area has to be greater than 0.334. So now look at this. I can now say without any matter of fact, everything is precise now that my area is at least 0.33. I can say that that's accurate. Why? Because I agree to 2 decimal places. Now if I shift up to 1,000, and hopefully you guys can see what's happening here. I now get 0.333, and I'm going to do some more decimals now. 8335. And then if I do the lower estimate, I get 0.3328335. So look how close these numbers are. And the last thing I'll do is 10,000. And hopefully you are convinced what's happening now. So if I do 10,000 rectangles, now clearly I'm not adding all these up. I'm having a computer do it for me. I hope you guys realize that. But I am starting to see the moral here, which I'm going to write on the right-hand side. Here is our conjecture. A is equal to what? Well, it looks like the more I do this, the pattern is that I'm going to get 1/3. Does anybody have a question about this? I know we're rushing. I feel bad at the end, but this is life. This is life in quarantine. And for that, I apologize. Does anybody have a question, a comment, a concern? I really hope you study this example. We're going to show you all these shortcuts I took next time we meet. So don't stress about this. There's lots of shortcuts that I'm using, and I'll show you about them next time. Any questions?
So for practice at 7, do you think you can open on Canvas, right? We can submit the assignment on 7. Do you think you can?
Just send me an email for that if you can.
I mean, I did send you an email, but I don't think you received it. Like I sent you twice.
Okay, well, what makes you think I didn't receive it? Because also
Uh,
stop recording, but just because I didn't. You talking about because your grade's not updated yet?